In the previous lecture, we saw minimal polynomials and I stated the Cayley-Hamilton theorem. Now, there are different proofs for the Cayley-Hamilton theorem, and many of them use what is called the classical adjoint, or sometimes called the adjugate of a matrix. Now, I'll give a slightly different proof using triangular matrices, because it also introduces a new concept and useful similarity property. So in this lecture, we'll explore similarity of matrices in more detail. We'll explore triangulability of matrices, and in the next lecture, I'll complete the proof of the Cayley-Hamilton theorem. So let's take a second look at similarity of matrices. I defined two n by n matrices A and B are similar. So given n by n, B is n by n. So we say that A and B are similar if we can find an invertible n by n matrix P such that A can be written as P times B times P inverse. Right? Now, what does this geometrically imply? This geometrically implies a change of basis, and that is what we'll see in detail in this lecture. Right? So to understand that similarity is equivalent to a change of basis, we must first understand what does a matrix represent. Now, matrix is one representation of a linear transformation, and it is the linear transformation relative to some basis. And in particular, in general, whenever we talk about a matrix A, we generally mean this to represent the linear transformation relative to the standard ordered basis. So let's see why that is the case. So now note that so a linear transformation is equivalent to matrix multiplication by a matrix A. So we can write y equal to A times x, where x and y are n by 1 vectors, right? So if we represent x in terms of, so we have x, this is x1, 2, up to n, right? Now this can be written as x1 times e1 plus x2 times e2, so on, xn times en, where ei is the ith standard ordered basis vector, which is the vector whose ith entry is 1 and all the other entries are 0, right? So let's see the effect of a linear transformation on this vector. So we have x, which is summation I going from 1 through n of xi ei. So this is the representation of x relative to the standard ordered basis e1 through en. Right? So if we look at a linear transformation operating on x, e of x, let's suppose that this is our vector y, right? Now this is some y1, y2 up to yn, right? So this is y1, y2 up to yn, and if we look at this, again can be written as y1 e1 plus y2 e2 plus so on plus yn en, right? And so now let's look at the effect of the transformation T on the ith ordered basis vector. Let's look at the effect on E1, right? So suppose that T of E1 is call this U1. So this is U1, U2 up to UN. Let's call it A1 because that will. Right, so suppose that T of E1 is equal to some vector A1, which is A1, A2, A11, A21 up to AN1. Right, and similarly, if T of EI is the vector AI, which is AI1, AI2 up to A1I, A2I up to ANI. Right? Okay, so let's suppose that this is the case. Suppose that T of E1 is equal to A1, T of EI is equal to the vector AI, which is A1I, A2I up to ANI. Right? So now let's see what y1, y2, y3 up to yn are in terms of these vectors AI. Right? So in general, if we have a matrix X, then T of X is summation. There is T of summation I going from 1 through n of xi ei, right? And y is some summation I going from 1 through n of yi I. Now, if these are the transformations of the standard ordered basis vectors E1, E2 up to En, then I claim that the matrix A, the transformation can be written as A11, A12 up to A1n, AN1, ANN. Right? Because note that when we multiply this by x, right, we get the matrix Y. Right, and that is indeed what we see here. Right, so effectively, this matrix A represents the linear transformation relative to the standard ordered basis. Right. So now, what if we want to study the linear transformation with respect to a different basis? So we want to see this relative to some basis other than the standard ordered basis. So let's suppose that we consider the basis which consists of vectors v1, v2 up to vn. Right, this could be an arbitrary basis. So if we look at the coefficient matrix, let's suppose that we have an arbitrary vector x, which is, say, some I going from 1 to n of alpha I vi. So relative to this basis, this can be represented as a vector alpha 1 through alpha n, which is the coefficient vector of x corresponding to the ordered basis v1, v2 up to vn. Right? So for the same vector x, you could have different. So for the same vector x, you could have different coefficient vectors depending on which basis you chose. So for example, if so this point in Rn, right, so let's suppose that this point is say 1 comma 2, this is 1 and 2, right. Now so this is the representation relative to the standard ordered basis. So corresponding to this point in R2, we have this vector. If we choose v1 to be the x-axis and v2 to be the y-axis, right? But on the other hand, if we were to choose v1 to be the y-axis and v2 to be x-axis, then the corresponding coefficient vector would be 2, 1, right? So the same vector can have different representations depending on which standard order, which basis you choose. Okay, so now let's go back to linear transformations. Our goal is to study the effect of the linear transformation in terms of some other basis, right? So effectively, if we are taking x, so let's suppose that t of x gives you some vector y. Now we want to write this not in terms of the standard ordered basis, but in terms of the basis v. So this is sum I going from 1 through n of beta I vi. Right? So we can represent y as a linear combination of the vi's, right? So our goal is to find this transformation. So if beta 1 through, we have beta 1 through beta n, so this is some matrix B times alpha 1 through alpha n, right? So we get another matrix equation, beta b equal to b times alpha, but this is the same linear, but this is the linear transformation T, but relative to this basis, right? And given an arbitrary linear transformation, you can have different matrices representing the same linear transformation depending on which standard order, which basis you choose. And we'll see that two given matrices represent the same linear transformation relative to different bases if and only if they're similar. Okay. So first let's see what is a linear transformation which represents a change of basis. So suppose that we have a vector x which has coefficients x1 through n relative to the standard ordered basis. Okay, so x1 through xn are the coefficients of x corresponding to the standard ordered basis vectors. Now we want to represent this in terms of a different basis, so we can also write, so this is summation I going from 1 through n of xi ei, but this can also be written as I going from 1 through n of alpha I, and our goal is to express the alpha i's in terms of the xi's and vice versa, right? So So this A is equal to alpha is equal to P times X, right? And what is P in terms of the V's? I want you to pause the video and think about this. Right. So the P can be represented in terms of V as the following matrix. So note that we have X, which is summation alpha I B I. So X is effectively equal to V1 Vn times alpha 1 alpha n, right? So this is V times alpha, where the ith column of V is where the ith column of the matrix V is the vector Vi, the ith basis vector Vi, right? And P is simply equal to V inverse. So this is V inverse times X, right? So given this, let's see what is let's see how similar matrices effectively correspond to a change of basis. So we have, suppose that relative to the standard ordered basis, we have the linear transformation A, and given any vector x, we have y is equal to A times x, right? Now relative to a different basis, say v1 through vn, we have, let's say, y prime, or sticking to our original notation, we have beta to be equal to b times alpha, right? So note that, so this is relative to the standard ordered basis, and this is relative to the basis v1 through vn, right? And our goal is to represent B in terms of A. So what is the relationship between A and B is what we want to address, right? So note that both of these represent the same linear transformation. So X and alpha are the same vector, but represented in terms of different bases. So X is the coefficient, is the n by 1 coefficient vector corresponding to some vector in Rn, and alpha is the same vector but the coefficients correspond, but it corresponds to the coefficients relative to the basis v1 through vn. Similarly, the transformed vector y is some vector in Rn, and the vector y1 through yn correspond to the coefficients relative to the standard ordered basis, whereas beta 1 through beta n represent the same vector as y, but this is now relative to the basis v1 through vn, right? So it's the same thing, it's the same vector, it's the same pair of vectors, but we are viewing this in terms of different bases, right? Okay, so now we want to get the relationship between A and B, right? But we just saw that x is equal to v times alpha, right? So x is equal to v times alpha, and similarly y is equal to v times beta, right? Because we're just, this is just a transformation from the basis v1 through vn to the standard ordered basis, right? And therefore we have y equal to A times X, or V beta equal to A V alpha, or beta to be equal to V inverse AV, right? And note that this holds for all particular or for all vectors alpha and beta. So for all vectors alpha in Rn, this particular relationship holds, and therefore this implies that the matrix B is equal to V inverse AV, right? Or A is equal to V is equal to VB V inverse, where the ith column of V represents the ith basis vector Vi. So this is a very important result, and we'll make extensive use of this particular observation in the coming results. Right. So to recapitulate, we have suppose that we're given a matrix A which represents a linear transformation relative to the standard ordered basis. Then if we want to represent the same linear transformation relative to some other basis v1 through vn, then the corresponding matrix B, then the matrix B is the same linear transformation relative to v1 through vn, and the relationship between A and B is A equal to VB V inverse, where the ith column of V is equal to the ith basis vector Vi. So effectively, what can we say about diagonalizability? So recall that if a matrix is diagonalizable if and only if there exists a basis of eigenvectors. So there exists an eigenbasis, and what diagonalizability implies that is that if we have v1 through vn to be a basis of eigenvectors, then the matrix A can be written as V E v1 through vn inverse, right? So, and this is true because the matrix D, so relative to the eigenbasis, the linear transformation is basically a diagonal matrix, right? So effectively what we're doing is that we have a vector x, right? We can transform this by V inverse to express the same vector in terms of the eigenbasis, and we apply the linear transformation. Let's call the linear transformation to be T, and the linear transformation, since this is in terms of the eigenbasis, this is a diagonal matrix, and we get the matrix beta, and when we transform this back, so this is V inverse, this is V, to bring it back to the standard ordered basis. Okay, so now so this is another way to view diagonalizability in terms of a change of basis, right? But we've seen that not every matrix is diagonalizable. Given a square matrix A, it is diagonalizable if and only if we can find an entire basis of eigenvectors for Rn. But as it turns out, every square matrix is triangulable. And what do I mean by that? Every matrix is similar to an upper triangular matrix, right? So even though you may not be able to diagonalize a particular matrix, we can always represent a matrix in terms of a triangular matrix. And to understand this concept, we introduce the notion of a fan. So suppose that we have a linear transformation A, which is a linear transformation which is represented by a matrix A. Then we say that a sequence of subspaces V1, V2, V3 up to Vn, so these are subspaces of Rn, and V1 is a subspace of V2, V2 is a subspace of V3, and so on. So this sequence of subspaces is a fan for A if the following two properties hold. So firstly, the dimension of Vi is equal to I, and the linear, when the linear transformation is applied on the particular subspace, you get back the original subspace or something within it. So this means that for all x in Vi, A times x is also in Vi. So the linear transformation cannot take a point from within the subspace to a point outside it. So effectively we have Rn right. So you have the linear transformation taking Rn to Rn, and you have the sequence of subspaces. So this is V1, this entire region is V2, this region is V3, and so on. Similarly, you have V1, and V2, and V3, and so on. So if you take any point within V1 and you take the linear transformation, it lies in this particular region. Similarly, if you take any point here in this region and you take the linear transformation, it lies in V2 itself. So it could lie strictly within V2. So it's possible that every point in V2 is mapped to a point in V1, but it's definitely within V2. You can't go outside V2. And similarly, every point in V3 is mapped to points in V3 only. So this is a fan, and we say that a basis is a fan basis. So given a fan for a linear transformation, we say that a basis V1 through Vn is a fan basis for this transformation if V1 through Vi forms a basis for the ith subspace script Vi. And from this it should be obvious that a fan basis always exists. So if we are given a fan for A, then finding a fan basis is easy. And how do we do that? So let's start with V1. So pick any vector in V1, right? So that forms the fan basis for V1. For V2, we want to find a basis for V2. So we have V1, which is anyway in V2. Right? So V1 is a subspace of V2, and pick any vector which is linearly independent with V1. Pick any vector in V2 which is linearly independent of this particular vector. Call it little v2. So obviously this spans script v2 and therefore this forms a basis. Right? So similarly for v3 we have v1, v2, v1, v2. Now pick any vector which lies outside the span of these two vectors but still within this subspace. Call it v3. So this forms a fan. So v1, so similarly we can do this iteratively, and v1, v2, v3 up to vn will form a fan basis for the matrix A. Okay, so the nice property of a fan basis is that the matrix, the linear transformation relative to the fan basis is always an upper triangular matrix. So if v1, v2 up to vn is a fan basis for A, then the linear transformation of corresponding to A relative to the fan basis is an upper triangular matrix. And why is that? So recall that, so we have y equal to a times x and beta equal to b times alpha. Now an important property to note is that the ijth entry of beta is equal to take the transformation of vi, you take the transformation of vj and look at the ith coordinate, right? So this gives you bij. Similarly, aij is the transformation of ej and the ith coordinate. Okay, so now if you look at, so since this is a fan basis, note that so t of v1 is obviously lies in v1, right? So therefore t of v1 is going to be some alpha, just going to be beta 1 times v1. And if you look at t of v2, then this is going to lie in v2. So t of v2 is going to be beta 1 times v1 plus beta 2 times, let's call it beta 1 1, beta 1 2 times v1 plus beta 2 1 times v2. Similarly, t of v3 is in script v3. So t of v3 is say beta 1 3 v3, sorry, beta 1 3 v1 plus beta 2 3 v2 plus beta 3 3 v3, right? So if you look at the matrix B, right, so we get beta 1 1 0, right? And this is going to be beta 1 2, beta 2 2, 0, beta 1 3, beta 2 3, 0, so on. Right? So therefore the matrix is always upper triangular. So what we effectively shown is that given a linear transformation A, if we can find a fan, then we can always find a fan basis, and with respect to the fan basis, the matrix is always a triangular and upper triangular matrix. But what is non-trivial at this point is, given an arbitrary linear transformation, can we always find such a sequence of subspaces? Can we always find a fan for A? And that is what we will address in the next lecture, and we'll use this to prove the Cayley-Hamilton theorem.